So,
Grabando.
okay, so good afternoon again, everybody. So now we are going to the second talk of this afternoon. Now we have Professor Robert Lipton from Louisiana State University, the US. So Professor Robert is an expert in multi-scale analysis, and he is working on this field for many years, and he's a well-known applied mathematician. So we are having this opportunity this afternoon to have seen him here. And Professor Robert is editor of several journals. For instance, he's the editor-in-chief of Science Journal on Mathematical Analysis, and IMA Journal, and Applicable Analysis. So, and his CV is huge, so it's difficult to say all his accomplishments. So, Professor, it's a pleasure to have you here this afternoon talking to us about fracture. So thank you very much for this opportunity, and hopefully soon in-person seminar.
Thank you very much. Thank you for your kind introduction, and it's a privilege to be here, and again among all these wonderful speakers. So thank you again. Today I'll talk about fracture phenomena. It's been around for quite a while now. Let's see here. Make sure I can. There we go. And this is joint work with Devdeep Bhattacharya and Prashant Jha in two separate publications. Just an overview of what I'll be talking about today. In particular, I'll be talking about non-local interactions across finite length scales. They basically have global consequences. So these non-local interactions occur across finite but very small length scales, but they do have global consequences. Just as a PDE does, you're taking a difference quotient, and that's an infinitely small but it's still non-local. And of course, we have solutions of initial boundary value problems, and these are the global consequences. So similarly, you would expect then the same. What is interesting, though, is when you make the non-locality finite but small, you can start to model flocking amongst leaderless schools of fish, birds, and these are sort of the emergence of a phenomenon. So one particular and very similar mathematical model for the flocking is the Cucker-Smale model. And there it involves a sort of a velocity being non-locally influenced by other velocities of particles nearby. Today, we'll be concerned with fracture, also viewed as an emergent phenomena and modeled through non-local interactions. Here, the non-local interaction will be displacements. So a displacement between nearby particles will influence displacements. So but mathematically, otherwise, there is no difference between the two models, which is rather interesting. Global fracture, we'll see from this model, emerges from the non-local dynamics. And this was seen by in the paradynamic models introduced by Stuart Silling back in 2000. So he saw that, when you allowed particles to interact non-locally, you would get, and dynamically, you would get emergent behavior. We know from the Leonard-Jones potential and various scaling arguments, upscaling arguments using gamma convergence, notably the wonderful work of Andrea Brady's, and also the incisive work of Adrian Liu, Brady's, and Michael Ortiz, that the fracture energies at the atomic level can be now seen to be, through the miracle of gamma convergence, emerge as a Griffith fracture energy. So these non-local potential energies at the atomistic level through gamma convergence can be recovered at the macro scale as Griffith fracture energies. And the Griffith fracture energy was introduced back in the 20s and now is a staple of the modern theory of fracture mechanics. And so very interesting connections being made here. So I'm going to continue trying to make some new connections. And basically, again, we'll talk about non-local methods as a field theory, and I'll explain that in a minute, for the free fracture problem. Free fracture problem means we need to determine the location and time of a crack in addition to the elastic fields or fields surrounding the crack. So we want to find both of these things, where the crack is, how it evolves, and its interaction with the elastic fields, and vice versa, the interaction on the crack by the elastic fields, because they could be used to steer the crack, a control problem. However, right now we need to get the forward problem down and feel comfortable with it first before we attempt a control problem. But this is what's happening right now, is we would like to get the forward problem nailed down. If we can do that to our satisfaction and to experimentalist satisfaction, then we can start learning how to mathematically control. What I'm going to talk about today is a forward problem. It will deliver as an initial boundary value problem. It will give you a pair, a deformation field and fracture set pair as output. So input will be initial conditions. It will be mediated by Newton's force equals mass times acceleration. And on output, you'll get a deformation fracture set pair. That's the idea. And here I've pictured in this picture here, I've shown a Liberty ship, which used to haul oil on the eastern seaboard of the United States. And it was just sitting in dock and it cracked on its own volition. And that's not a good thing. And so it's good to understand fracture. And so back in the day, what they realized is that they needed to make thicker hulls, and then that wouldn't happen. Okay, so we're going to discuss some new perspectives on the nonlinear or non-local dynamic modeling. Again, the second bullet here is we'll formulate it as a well-posed initial value problem for the displacement. On output, we'll get a fracture set displacement pair, and I'll explain. The fracture set will depend on the actual displacement itself. The energy balance, we will recover an energy balance between the deformation energy, the kinetic energy, and the failure energy, and the energy put into the system. So we will be able to account for all the energies of the problem. The problem will be formulated. The dynamics will be based on F equals ma, and it will be complemented by initial conditions and natural boundary conditions. One advantage of this formulation, we do this on purpose to formulate it a certain way, is such that the failure energy density turns out to be a two-dimensional integral as opposed to a volume integral. And this is for three-dimensional problems. For two-dimensional problems, it's a one-dimensional integral. So the energy turns out to be a one-dimensional integral. Now, going into it, we do not assume that a fracture is one-dimensional. We do not assume we don't even assume a fracture. We just assume some sort of damage, and then it evolves into a fracture. Or if damage occurs, it may not even occur. You just may have a linear elastic material in an initial boundary value problem, and you just see elasticity, linear elasticity. On the other hand, if the specimen is loaded such that drastic loads are applied, you may then see the emergence of a crack as part of the dynamics. Interestingly enough, the failure energy for a flat crack gives you back the classic Griffith fracture energy, which is critical energy release rate multiplied by the length of the crack. And what's very nice about all of this is you don't have to try too hard to understand, where the energy of fracture goes. Everything that I'll talk about today, energy balance and all the conservation laws follow, as you would expect, by multiplication of the equation F equals ma by the velocity and integration by parts over the domain. So here's a picture of a domain, omega. And so what we would like to do is here I've pictured the equation of dynamics, force equals ma. So the acceleration here is the second derivative of the deformation field, which is boldface u. So the deformation field depends on time and location within the domain, and then rho will be the density. Here we'll just assume always the same material everywhere. And then that is set equal to the elastic or particle force on particle due to the deformation that I'll call L, calligraphy L, and it depends on space and time. And then an applied body force, where the body force is applied within the sample. Usually it'll be a small layer of body force near the boundary. So we approximate boundary loads this way. Then initially we have at t equals 0, we have the deformation equal to some initial deformation, and then also the initial velocity, that's u dot at t equals 0, is equal to some prescribed velocity. And what we'll discuss is the length scale of non-locality, that's the epsilon, and I'll discuss that as we move forward. And the goal here is to design the forward problem or design the non-local operator L, and in such a way that we recover a well-posed initial problem. Right now it's an ODE on Banach space, and then well-posed, and then from this equation, we can derive our energy balance. So we go back a little bit, back up a little bit, and we start with this paradynamic formulation introduced by Stuart Silling. And the way paradynamics works is it formulates an evolution equation for U, the U field, of the form F equals ma. And the key is when the strain between 2 points passes a threshold, then the force, non-local force from one point acting on the other becomes 0. And this force acting between 2 points separated by a little bit is called a bond. And so when the force goes to 0, we say we've broke the bond, okay? And then what happens is if you break enough bonds, during the course of your evolution of your displacement, fractures and defects can emerge from the simulation. So that's it kind of hangs together logically. And so paradynamics breaks bonds as part of the evolution of the deformation. So that's the setup, 30,000 foot, now the devil, of course, is in the details. And so what we're going to do as mathematicians is we're going to really parse the details and make sure we're going to get the details right. Okay. And in fact, in doing so, we actually wind up with a slightly different model, but we're going to try to do the details right. Okay. So what we're going to do is we're going to formulate it, because as was formulated back then, it was not a well-posed initial value problem. So we're going to formulate it as a well-posed initial value problem. And we are going to, from that initial value problem, we can multiply the equation of dynamics by the velocity, integrate by parts, and from that, we can get energy balance. And from that, we discover, we did not build this in, we discover that the energy expended to break bonds is supported on a D-1 dimensional set. So if you're in three-dimensional body, it's a surface, a two-dimensional set, or if you're looking at plane strain fracture problems, that's a two-dimensional problem. Your energy is supported on a, if you will, a crack on a one-dimensional set. And so we will see this in a minute. Okay, so the currency of paradynamics is really, the zone of interaction, of force interaction. And so for each X in the body, here I've shown it here as the center of a disk of radius epsilon, we have points Y within that disk. And this is the disk in which forces can interact. If Y happens to be outside the disk, it does not affect X. However, if Y is inside the disk, it does. Okay. Okay, so we only interact between 2 points within an epsilon neighborhood, and we will be taking epsilon, this length scale, small relative to the length scale of the body itself. And we can formulate this problem in 2 or 3 dimensions. In 2 dimensions, really a disk. H, epsilon, is really a disk centered at centered at X. And in 3 dimensions, it's a ball centered at X of radius epsilon. So once we have our 2 points, then what we do is we look at the deformation field U at one of the points Y and U at the center point of this disk X. And we take their difference and divide by the distance between X and Y. So that's a gradient, a difference quotient. And we resolve it along the direction X, Y minus X. Okay, and that's where E is. So we take that difference quotient dot product with the direction vector E, which is just the direction Y minus X. Okay, and then what we do is we take, and you see here this dark F in right below here, this dark F here. That takes as its argument the strain. And we suitably rescale it. We'll come back to that. But it takes as its argument the strain. So the force between the point X and Y is a function F of the strain. And this is our constitutive law. That is, it relates force to strain. Now, I'm going to talk a bit about what our constitutive law is, but for the moment, you can see, okay, fine. And then we have pre-multiplying it a gamma, which also depends on the displacement, and we'll explain how it depends on the displacement in a minute. But the key is that gamma takes values between 0 and 1. And so when gamma is 0, we do not see the force because it's 0 times the force. The force has been, rendered irrelevant because there's no material. Well, not no material, but the bond is broken. Now we have to have a rule for breaking bonds, but the bond is broken. When gamma is 1, the bond is perfectly intact and the force is able to act. Okay, so, and then what we do is we fix X and we take the integral, we average over all Y's inside that ball. And so that's our model. And what we have done, though, interestingly enough, is gamma can be thought of as a phase field, taking the value 1 in intact material and 0 when the bond is not intact. And it's coupled to the force, okay? And what I would like to say is that this is a coupling, and then it's integrated. And so it's a multiplicative coupling of phase field. Well, don't want to do that. It's a multiplicative coupling of phase field and force. And then we integrate it around the domain. And that's how we couple phase field to force. for those people who may be familiar with the model of phase field model of fracture, that coupling is done through a different means. It's done through what is called an Ambrosio-Tortorelli coupling, which is really a Modica-Mortola coupling. For those of you who work on free boundaries and phase changes, but it's different than that. This is a real, we basically couple by multiplication and then integrating. Okay, so the force between the 2 points is again this dark F, and it depends on the strain, suitably rescaled, and that rescaling is very handy. The bond again is said to be broken when the force is 0. So we're going to have a force that somehow is elastic for small strains and then breaks for large strains. Okay, and the phase field also depends on the strain, and it starts at 1, it's unbroken, it's intact, and it goes to 0 when the strain gets too big. Okay, so this is how we sort of couple the material to the force. Okay, so here the phase field, this phase field here, this gamma, is the rescaled strain. And what we do is we take gamma and write it as a function composed of the maximum strain up to time t for the 2 points fixed, x and y. And this is all due to u, the deformation. So this type of composition, h here, will go from 1, it's almost a step function. It'll go from 1 to 0, but it'll go from 1 to 0 gradually instead of abruptly like a step function. Okay, and so the degradation function h is coordinated with the bond force, and you'll see it 2 slides from now. Okay, so here is the force. The bond force F will be given by this G prime, and it will be a function of the rescaled strain. So this here is the bond force. This, when R, that's the rescaled strain, is negative, when the strain is compressive, the force resists compression, as it should. You don't want material to interpenetrate. On the other hand, when you start stretching it, okay, fine, it's linear elastic, but then at RC, it flattens out. That's the maximum strength of the bond between X and Y. That's what we call the maximum strength. And then it becomes unstable, and at R plus, we break it. And that's the coordination of this H function and this F function. So that is shown here. We get past right at this point here, that's where the force is 0, and then we break it at R plus, just a little bit beyond that. And we'd like to use a heaviside step function, but it's easier, and you can take derivatives if you use a little bit less than 1. Okay, it's mathematically well posed. So what is the failure set then? The failure set is this collection of pairs, X and Y, such that the force between them, or the bond between them, has been broken at some time, tau, in the past. Okay, and the past could even also be current. So at some point, you broke the bond, either at a remote time in history, or you just did right now, instantaneously. And so we collect these bonds in a set, and we'll call it gamma epsilon, and those will be the pairs for which this 2-point phase field has gone to 0. And we give that set gamma epsilon an indicator function, 1 if you're a pair belonging to that set, 0 otherwise. Okay, that's helpful. Now, what we can do is we actually have now our equation of motion, which is given, I'll just go back and just say we've defined everything now. Okay, so here's our equation of motion, and what we're going to do is we're going to take that and multiply by the velocity, integrate by parts, and then see what happens. So we multiply by velocity and integrate, and we discover that we have the time derivative of kinetic energy here. We have the velocity multiply the force, the L operator, and we integrate over the domain, and then we have our right-hand side multiplied by the velocity. And once we integrate by parts, we get this relation, this identity, because we start with an equality, we still have an inequality. Then we work on the second term, and we work on the second term, and we learn that before we do the second, we work on the second term, but before I rewrite the second term, I identify these following energies: the kinetic energy, the elastic energy, which is just this is the potential, this is the force potential right here, multiplied by the quality, the phase field. If it's 0, you notice we don't have elastic energy there. So if gamma is 0, we don't have any elastic energy because we have no material. Okay. And then the damage energy is written as the time change of the phase field, and then integrated over time, multiplied by the current or the over historical potential at that time. And adding all the energies gives the energy balance. Okay, so we have energy balance. Now what I'd like to do is I'd like to go back. So this is what we have. This is very nice. So this is we got this. We got this. So this is obtained from our equation of motion. And now we would like to kind of clean up this D. That is, can we identify this damage energy a little bit better? And so we can. So we can and we do. And what we find is the damage energy can be written as 1 minus the phase field times this kernel, which is basically used to write, just localize the integral. So here the integral is localized to the horizon, the ball centered at x, and then that we do the second integral, and then we get an integral over the body, and we get our damage energy. But our damage energy is this very simple form, and C represents the total energy underneath, or the total area underneath the force potential when the force potential is positive. Okay, or the total under the force, the total energy under the force, and for straining forces, and that's C plus. And so we from that we can then just say, well, suppose gamma is 0. When we set gamma to 0, then we get the failure energy. This is the failure energy. And what is amazing about this is that the failure energy is in fact a D-1 dimensional measure. And so we can use a little bit of geometric measure theory, and we see that the D-1 dimensional integral is of this form 4, where M is associated with a line segment. So we use the slicing decomposition of the domain, which is used in understanding the special functions of bounded deformation and their fine properties. We use that slicing decomposition, rewrite that failure energy, and we come up with 4. We apply Grunwald's inequality to our ODE formulation and show that this energy is bounded by the energy applied to the body. And flat crack geometries, because we will be able to compute this energy, this failure energy, explicitly for flat cracks, show that this failure energy, even though it's supported on a D-1 dimensional set, has positive energy. So it's bounded and concentrates, it is concentrated on a D-1 dimensional set, but still it's non-zero. But it's also not infinite by Grunwald's inequality. So what I'm able to do then, what we're able to do then is we go ahead and we compute what is a common quantity in fraction mechanics called the critical energy release rate. And it's the energy required to separate or send all bonds, to break all bonds, or have force go to zero between points above a horizontal crack and below a horizontal crack. So in this picture here, this line is a horizontal crack. This is above a horizontal crack. This is a point X below the crack, and I want to break bonds that happen to be any point C above the crack within this loon. And then what I do is I take X and I send it to epsilon away, epsilon units below. So I do these integrals, and then I add them up, each one for each X, for X going to epsilon. And then I get a whole integral there, and that integral is nothing but this. I evaluate it, and it's the critical, what we call the critical energy release rate, which is the energy required to break all bonds below and above the crack. And we can apply Crofton's formula from geometric measure theory to our integral. And we find that if we have a crack CT of, say, area given by this d minus 1 dimensional Hausdorff measure, which is just the area integral of CT, multiplied by the GC, you get the fracture energy, you get the failure energy. And this is nothing but Griffith's fracture energy. So for a flat crack, we just automatically get back Griffith's fracture energy. For curved or kink cracks, if we take epsilon to 0, we also get back the Griffith's fracture energy, provided we have rectifiable cracks. That is, cracks with finite length. And that's what I do here. And so this is basically, this is basically kind of elaborates on this using the geometric measure theory. And so this is sort of how it goes, how it follows. The other thing is this is where that square root times strain scaling comes in. When you use that, you then get, when the strain is very low, you get that the stress is related to strain through the elasticity moduli, through a mu, which is a shear moduli, which is also equal to the Lemay moduli lambda. This is a Poisson ratio 1/4 material in 3 dimensions, a Poisson ratio 1/3 material in 2 dimensions. And this is because we're only considering bonds, forces between 2 points. If we looked at 3-point potentials, then all of a sudden we would be able to do more general Poisson ratios. That's for future work. Right now, we just wanted to get it right for 2 points and show the connection to elasticity and classical fracture theory. So all of this so far has been showing, crack energy is consistent with the Griffith energy, but in reality, crack energy is determined by the dynamics, and basically and more specifically, where the cracks are made. So the cracks are always growing from their tips. So that's where cracks are made. It's from crack tips. If you understand the growth of crack tips, then you understand the growth of cracks. So along these lines, we recall that the derivative of the phase field is at 2-point phase field is positive and non-zero on the complement of the fracture set. The set of pairs X and Y for which this is non-zero, which the derivative is non-zero, is called the process zone, and that should correspond to the crack tips. And we have here then that the dt, the change in the damage, is given by the change in gamma. Okay, and so our power balance then we actually can, write a power balance instead of energy balance. We take the derivatives of everything, and we have our power balance, which says that the change in damage is equal to the energy put into the system minus the kinetic energy and minus the elastic energy. And what's important here is that this time derivative is non-negative. With that in mind, we can actually say something. That is if the rate of energy, we can actually say, if the rate of energy put into the system exceeds the material's capacity to generate kinetic energy and elastic energy through displacement and velocity, then damage and fracture occurs. Okay, so we're actually able to say something, and based on mathematics, not based on philosophy. This has nothing to do with philosophy. This has everything to do with rigorous mathematics and the formulation of a well-posed boundary value problem. We can also discuss energy balance and parse it more finely. Last, I want to, because I have very few minutes left, and so I want to make sure I wrap up in time, is that what I would like to show you is that as epsilon, the horizon of non-locality, the interaction of non-locality, goes to 0, the fields surrounding a crack go to a limit field, and the limit field actually solves the linear elastic wave equation, or just the wave equation. So the crack itself, if we know it's propagating, say, here in this picture, from left to right, if the crack is propagating from left to right, the limit crack also propagates from left to right. It is now, just a Schlitt domain with the crack propagating, and around it, we have the solution of the linear elastic wave equation. So we have two things occurring. We have a growing boundary interacting with the solutions of a wave equation, or conversely, the solutions of a wave equation are working on influencing crack growth for a growing crack. So here we have this two-way coupling now, okay? So this is the interesting thing. So here is just a slide saying how you would calibrate it to measured quantities, that you would get from your off Wikipedia or from experiment. And then using those, you would plug in and calibrate your non-local model. You can do that. And we typically choose our horizon epsilon to be smaller. This is the usual Griffith criterion of sort of like an asperity being less than this ratio here. And so these are the GC is where we computed that. The E is the Young's modulus, which can be picked off a table. The sigma F is the failure. That's where it softens, starts to soften, that force strain loss starts to soften. And so all of these can be obtained from sigma F from experiment, GC also from experiment, and E from experiment, and we can plug them in, and then that's how big we're going to take our horizon relative to the length scale of the domain. And so I'm just going to show you some numerical solutions, because once we have a well-posed initial value problem, we can discretize and approximate it with a finite difference model. And so here, Deb Deep has done some of these simulations, and basically what we're doing is we're pulling on the top and the bottom, and we're pulling like we start at t equals 0, and then we start immediately at just a skosh, an infinitesimal time later, start pulling up, and on the up face and down on the downside, and then the left and right sides are traction free. And this mimics the experiment of Buchbinder and Feinberg, and where they take a material and they pull it, and then they take a razor blade and slice it. So here instead we put a pre-notch in, and at a time later we pull on it. So what we see in the up two panels, on the two top panels, is we pull on it not as hard as we pull on it in the two bottom panels. So in the two top panels, we pull on it and we see that the crack starts to propagate from the left to the right. Here we can notice that it's a crack, as evidenced by this is a displacement fields above and below. And you can see in front, the displacement field is nice and continuous. Then the bottom two panels show, again, we pull above and below, and the crack, again, starts to propagate. And we can see the crack tip, and see in front of the crack tip, it's nice and continuous. The displacement field is nice and continuous. But behind the crack tip, it's not. It is cracked. And this sort of releases energy. There's not as much energy anymore. It's sort of the shadow of the crack tip, and now we don't have so much stress in the top flat panel, or in the top part, in the bottom part of this panel. So the stress here between here and here is much less than the stress here, but we crack to relieve the stress. And here, if we pull on it too hard, the crack could be unstable and split into two. So what we do is we go ahead and we take a horizon X. We take X, a point in the body, and what we do then is, for that point, we assign a number. And that number will be the maximum stress seen in that neighborhood centered at X. And here the stress is related relative to the critical stress, which is the stress in which the force became flat and then started to decay. So we take that ratio and we look at the max of that, and we can plot at each point X surfaces of Z. And what we see is that we've thresholded here. And so we're only plotting these lines here that you see are level lines of this function Z, but they've been thresholded. We aren't drawing all the level lines here, just level lines above a certain value. And you see that they're focused, maintaining these level lines, they're focused at the tip of the crack. And again, when the crack bifurcates, which is the bottom two panels, ultimately it bifurcates again. We see that it's concentrated there. Similarly, we can look at the strain energy in the undamaged material. Again, for each X, we can plot a number, and then we can take the iso lines of that number. And so this is the strain energy density in the undamaged material. And this rho epsilon is basically just enforcing that we only look at Y's near the horizon, not Y's away from the horizon. So that rho is just a kernel that just is non-zero inside the ball of radius epsilon, or disk of radius epsilon. And so this is the energy density. And again, we see the energy density is actually maximized just in front of the crack tip, just in front of the crack tip. And even when we apply more force such that it splits, it's still concentrated just up in front. And this is consistent with the experimental results of Bachbinder and Feinberg, reported in we have this in our references and also in the extended abstract in physical review letters. And so I'll just say that using methods of weak convergence, sending the horizon to zero, we can show that in the limit, as the horizon goes to zero, we go towards a target function, U0, and we have the displacement, velocity, and acceleration in the various topologies of weak convergence. But we find that off the crack, the target function, I mean, in the whole domain, it's SBD with jump set localized to the crack itself. And outside the crack, which is also a one-dimensional thing. So if we're in 2 dimensions, it's just the Hausdorff, it's just the H1 Sobolev norm of dt, the domains, the Schleidt domain. And we also have 0 traction on the crack flanks. We find that this is true. And so we find that we agree actually with the solutions of Dalmanzo and Rodica-Twatter was reported in Journal of Differential Equations in 2019. And here's a picture again of more general loading. We're again pulling from the top and the bottom. The crack gets attracted to this hole and then comes out, emerges from the other side. So with that, I'd like to conclude.
Professor, thank you very
Yes, sir.
much. We open now the microphone for questions and comments. If anybody wants to ask, you have the microphone open, or you can write in the chat. You can write it either in Portuguese, Spanish, or English, so we can translate. Pessoal, se alguém quiser alguma pergunta, pode perguntar no chat, tá? Em português ou em espanhol. Okay. Professor, I have a small, curious question, actually. Would it be natural? I mean, it would be, but would it be possible to try to control the crack somehow, like maybe the size or the energy? I don't know.
Yeah. So the answer is yes. And what's fun is there is and I'll remember his name in a minute. I met him. We had recently an Ober-Wolfach meeting. We organized an Ober-Wolfach meeting on fracture, and I can provide his name. So what he did was he did experiments where he would, if you imagine, these software that you get to train pilots, where you have this feedback control and you drive a plane, a flight simulator. And so he took, and he had to write his own software and design his own machinery, but it was basically a crack. It would use the technology of feedback to guide a growing crack in a field of, say, inclusions, and make it turn and bend and weave in various ways. So this was done already experimentally, okay? And so the answer I have is a resounding yes. The question is then, fine, you can do this, so you should be able to do the forward problem mathematically. Once you are happy with your forward problem, yes, the answer is yes, you can start to do control. And this would be a wonderful thing.
Okay, yes, because for instance, I don't know if maybe physically, because for instance, in the case of the ship that you showed, maybe you don't want to maybe avoid the crack because maybe it's impossible, but maybe you can try to let the crack be somewhere where you know it's safe to for it to happen, maybe somehow, or something, or maybe the size. You can just control the size so it's somewhere safe and not big enough. I don't know. So yeah, there are many things that. But what I don't understand, like, what would be? Do you think what could be the control in that case in your dynamical system? Where could it enter? Because you have your system, but I wouldn't know where to put the control. Let's say, how would it enter in the equation?
Yeah. So you could have it done passively or actively. So actively, you would do it very much like this fellow seems to be doing through the loading. You can figure out how to load your sample such as to how to guide the crack. That is the sort of the active way. The other passive way is to put in heterogeneity at various points to influence the elastic field in the body. Once you have an elastic field, you can then interact with the crack. So this is the wonderful thing. Your crack modeling is only good as your elasticity modeling. So the elastic field can be used to guide the crack. So one crude way to generate elastic field is through body forces and create different scenarios, for elastic forces to occur in response to a load. And that way you guide a crack. And then the other way that I know of is to introduce an inclusion by itself. By its very geometry, it will induce a stress field which can then be used to influence a crack. And both of these are used right now in a very informal basis, okay? But in a very informal basis for attempting to, as you said, this Liberty ship, what they discovered is how to make sure no cracks will appear under a certain ensemble of loadings. And this was the major success of fracture mechanics from the 1950s on, or no, from the 1930s on. It was very crude, but they had various ways. Basically, they just wouldn't even tolerate having a crack. And how do you do that?
Okay. Thank you very much, Professor. So, any other question, comments? Okay, so if not, thank you, Professor Robert, and also Professor Kunish, because now we have a break, right, Juan? Tem